Okay, here we go. I'm going to go fast because it's Super Bowl Sunday. I'm missing the game. It's 7-0. Eagles. Anyway, Austin Reeves, featured athlete. He just scored his career high, 45 points. He's about to be an all-star one day. Anyway, a rectangle with area 12 square units is dilated by a scale factor of k. Find the area of the image for each given value of k. So what you do is you always do, you do your starting area times k squared equals your new area. Because the area is going to change by k squared, not just k. So if k equals 2, you start with 12. So 12 is always, A is always 12, your starting area. And you just do this equation. You just go 12, like A, times your scale factor 2 squared equals your new area. So 12 times 4 equals your new area. So the new area will be 48. That easy. Okay. What if k equals 5? So you go 5 squared equals new area. So 12 times 25 equals A prime. And 12 times 25 is 300. So 300 equals A prime. Now these are all square units, don't forget that. Okay, 12 times 1 squared equals A prime, so 12 times 1 equals A prime. So that one will just be 12. Okay, 12 times 1/4 squared will equal A prime, so you'll get 12. And then you just do 1 squared over 4 squared equals A prime. So you'll do 12 times 1 over 16 equals A prime. So that finally equals 12/16, or take a 4 out of each, 3/4. So your new area is going to be 3/4. Okay, 12 times 1.2 squared will equal A prime. So 12 times, that should be 1.44 equals A prime. 1.44 times 12 should be 17.28 equals A prime. Now these are all square units. Don't forget that. Okay, the area of a circle of radius 1 is pi units squared. So pi is like A. Use scaling to explain why the area of a circle of radius r is pi r squared. So what you do, so here's with 1, anything here is r. So if this one is pi, then the radius, say the radius was 3, well that's 3 times as big, so that would be pi times 3 squared, so it would be 9 pi. But whatever the r is, that's how you scale it. So it starts with 1, r is, you're going to multiply by whatever the radius is, so it'll just be pi r squared. All right, because the scaling changes by r, so you multiply the original A times whatever like your scale factor is. Okay, trapezoid AB, A prime, B prime, C prime, D prime was created by dilating trapezoid ABCD. So this big one was created by dilating ABCD in blue, using D as the center of dilation. What was the scale factor of dilation? Okay, so this one is 4, right? AD, 4 units, 1, 2, 3, 4. And then we've got 5, 6, 7, 8, 9, 10, 11, 12. So it's looking like the scale factor is 3. Okay, based on the scale factor, how many copies of ABCD including the original, should fit inside A prime, B prime, C prime, D prime. My guess is 9, but let's see. Including the original. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's see. Why does that seem off? Oh, I know why. 1, 2, 3, 4, 5, 6, 7, 8, and then the orange is 9. So yeah, how many copies? 9 or 3 squared, right? Because the scale factor is 3. Okay, how can you see your answer to these questions in the diagram? Well, if that's 1, 2, 3, 4, 5, 6, 7, and 8, and then these fit together as the 9th, there you go. There's 9 of them. See above with the 9 numbers. 9 numbered trapezoids. Again, going fast because it's Super Bowl Sunday. Each image shows a quadrilateral and a plane. Okay. Quadrilateral has been dilated using a center above the plane and a scale factor between 0 and 1. Estimate the scale factor that was used for each dilation. So when you have these dilations, this is scale factor 0, and then the bottom is always scale factor 1. So this is 0, this is 1, this is 1, this is 0. So we just got to estimate. Let's see. This looks like a scale factor of 3/4, so k equals 3/4. This one looks like k equals 1/4, and this looks like k equals 1/2. Yep. All right, and here's how you can really tell. This is, there's 1, 2, 3, 4, yep. And then from here to here, yeah, for sure. Yep. Okay, cool. Select the solid whose cross sections are dilations of some two-dimensional shape using a point directly above the shape as a center, and scale factors ranging from 0 to 1. They're looking for stuff that has an apex. That's what they're looking for. So cone, yep. Cube, nope. Cylinder, nope. Triangular prism, no. You might have been tricked by this one. That would have been a, oh, it's still like the solid. Okay, cool. So you needed the one that had the apex, and that's the cone. All right, select all figures for at least one cross section is a circle. This one's a piece of cake. Triangular pyramid, no. Square pyramid, no. Rectangular prism, no. Cube, no. Cone, yes. Cylinder, yes. Sphere, yes. EFG. If the two-dimensional figures are rotated around the vertical axes of rotation shown, which solids are formed? This one is going to be a cylinder, and this one's going to be a sphere. Easy. Okay, is that it? Do I get to go watch football? Nope, 2 more. Okay, Tyler and Jada wish to find the value of x, the length of side BC in this triangle. Tyler decides to set up the equation tan 56 equals 8 over x, right? Yeah, Tyler's good. Jada says she prefers an equation that has x in the numerator. So remember numerator, denominator, Notre Dame. So Notre Dame, football. Anyway, for numerator, what is an equation she could use instead? Well, you know this is 90. This and this have to add up to 90. So you know this is, let's see, 24? Let's see, 70, yeah, 24. Because 56 plus 20 is 76, no, 34. Jeez, I'm off today, I'm rushing. So this is 34 degrees. So you could do tan 34 equals op ADJ. So you could say tan 34 equals opposite x over 8. And then x would be on top, the numerator. So that would work. She doesn't want x on the bottom for whatever reason. So, okay, number 9, triangles ACD and BCD are isosceles. Angle DBC has a measure of 110. Okay. That means this and this are the same. There's 70 left, so that's 35 and 35. Because 110 plus 70 will be 180. Okay. That also means that let me think. Gosh, let's see. Oh, I know why. Okay. So that also means that these whole things are, these are the big ones, are the same angle measure. And each one of them is going to be, this one's going to be congruent. I'll show you why. This little guy will be congruent to this little guy because they're the same. They both equal ADC, angle ADC equals 35 plus ADB, right? And then ACD, angle ACD, also equals 35, and then plus ACB. We're talking about angles, right? Now you know that angle ADC equals angle ACD because it's a nice isosceles triangle, right? Now, if these equal each other, then you can set these equal to each other. You can say 35 plus angle ADB equals 35 plus angle ACB, right? Subtract 35 from both sides. These cancel out. So now you know angle ADB equals angle ACB, the two orange ones. And then you have side angle side, side angle side, meaning that this one equals this one. So ABC will equal ABD. And this is like a full circle. 360 minus 110 equals what, 250? So then each one of these is 125 because they're corresponding parts of congruent triangles. Now, find the measure of BAC, so we're almost there. Let's see. 35, 125. I need to figure out what this is. Let's see. How can I get that? Oh gosh, let's see. What are those whole angles? I'm trying to figure this out. I know I can get this. BAC. These are obviously congruent, corresponding parts of congruent triangles. Let me think. It's an angle bisector, I know that. Is there a way to determine if it's equilateral? Doesn't look like it. Let's see, 125. How do I get that? Blank in here. I can figure this out. Gosh, I'm blanking. AD congruent to AC, BD congruent to BC. Oh, BDA. BDA is a measure of 22. Jeez, they gave it to me. BDA is 22. So this is 22 also. Okay, so 125 plus 22 plus BAC equals 180. So you just got to subtract 125 and subtract 122. So here we go. On 180 minus 22 minus 125. This is 33 right here. So angle BAC equals 33 degrees. Come see me if you want further explanation. I gotta go watch Super Bowl. See you.